And it's my distinct pleasure at this time to introduce Professor Dawn Tilbury, who is a faculty in the College of Engineering in Mechanical Engineering and the Department of Electrical Engineering and Computer Science. And she marshals a group of about 20 faculty in the College of Engineering who all associate themselves with robotic research. And she is ideally suited to talk to us about the great things going on at the University of Michigan as far as robotics research is concerned. So please join me in welcoming Professor Tilbury.
Well, thank you very much. I was asked to come and talk to you a little bit, very briefly, about some of the exciting research that's going on in Michigan robotics. So I think I can figure out how to use this. Oh my goodness, the resolution is completely off. Anyways, so it looks so fine up here. Okay. So over the past few years, as Vineet mentioned, we've been meeting with a group of faculty, about 25 faculty across the College of Engineering. And those of you who aren't familiar with the acronyms, this is the Aerospace Engineering Department, the Biomedical Engineering Department, Civil and Environmental Engineering, Computer Science and Engineering, Electrical and Computer Engineering, Industrial and Operations Engineering, Mechanical Engineering, and Naval Architecture and Marine Engineering. So that's most of the departments in the college. I don't think there are any chemical engineers involved, at least not yet, but maybe soon. And just to give you a sense of kind of the breadth of the research that's going on across the whole College of Engineering in all these different areas of robotics. The college has emphasized that this is an important growth area for the college, and in the last several years we've hired a number of faculty in this area, and you can see the faculty that we've hired are in all different areas of robotics and in all different departments. So this is not an initiative from electrical engineering or mechanical engineering. This is really an initiative from the whole College of Engineering. Some of the people whose pictures you see there are here today, and you could maybe talk to them some more about their research. So what I'd like to do, I guess, now is talk very briefly. I have asked all these 25 faculty to send me one slide kind of summarizing their research interests, and so I'll kind of go through that very briefly to give you this sense of the breadth and depth of the research that's going on. So I'll start with Professor Gabor Aroz, who's been around here, and he has a poster over there. You can talk to him more. He's interested in looking at connected vehicles and how cars, as we talked this morning in the panel discussion, might talk to each other. What are the challenges when the bandwidth is limited and not all the information might get through? Or there'd be some delay in the communication when one car sends to another. How is that going to impact the performance? And in order to study this, he's building a test bed of small ground vehicles and using control strategies to emulate different types of powertrains as well as different types of cars on the road to enable this type of research. Very exciting things going on in that project. Continuing on with ground vehicles, I'll talk briefly about some of the work that Professor Olsoy is doing also in mechanical engineering. In the past, he's worked with Ford on a lot of active safety technologies, including lane following, as you can see on the left-hand side. And more recently, he's looked at obstacle avoidance technologies for ground robots, where the robot can use sensors to try to differentiate different types of moving obstacles from cars and pedestrians, and maybe give different weights to the two types of obstacles that it needs to avoid in order to plan its path, while taking into account the uncertainty that comes from all these different sensing technologies and still guaranteeing appropriate levels of performance. Another area in ground robotics is hazard avoidance, particularly rollover avoidance. When you try to push the limit for cars, you know that sometimes they can roll over, and autonomous vehicles are no exception. So if you're trying to drive an autonomous vehicle, how would you model its tendency to roll over as well as optimize its path through an obstacle field while minimizing its rollover potential? And this is something that Professor Stein is working on from mechanical engineering. You may have met Professor Olson here this morning. He's working with Ford on automotive safety technologies, particularly with planning and perception. So this is using some of the similar techniques that you heard about from Professor Brogi, but more merging different types of sensor information, including vision and LiDAR. A couple of years ago, Professor Olson won this MAGIC competition. This was the Multi-Autonomous Ground Vehicle International Competition in Australia, and his team of students from the University of Michigan won this competition in a great international field. You can see they even got to go out to the Chrysler Arena to receive their check of their award winning. So great connection between robotics and athletics. Now we're here in the stadium to celebrate robotics today. Professor Olson is working closely with Professor Eustace on this same type of automotive technology with Ford and perception. But Professor Eustace also uses the perception technology for underwater robots. He's built some underwater robots. You can see them down the hallway here that look at how would you inspect the hull of a ship to try to maybe find barnacles or bombs that might be on it, or to map out the environment in an underwater area such as Lake Michigan, try to find out where are the different ecoregions and plants and animals that you can find down underneath the water. So again, looking at perception technologies for mapping and navigation, both above the ground and below the ground. Moving from the ground, from the water to the air, we have Professor Ella Atkins, who actually has an interesting project with flying fish that live both on the water and in the air. And these robots are seaplanes that can float in the water until they reach the end of the area they're supposed to survey, and then they fly back to where they started before they drifted with the current. So really an integration of autonomous sea navigation, both in the water and in the air. She also has a number of different air vehicle operations. I think you might have seen some of them down on the field over lunch, including quadrotors and fixed wing and flapping wing drones. So really looking at safety and performance of these different types of vehicles. Going now from the air back to the ground, we have a number of activities in walking robots. You may have seen Mabel. She won the award recently as the world's fastest running robot with knees. She is attached to a boom, and so she can only walk around in a circle, but there are a lot of nonlinear control challenges that are required to make her walk and run. She has very limited sensing and really can't see where she's going. It's only a position and force feedback. Mabel is being retired and sent over to the Museum of Science and Industry in Chicago, and her successor is Marlowe. You see a picture of him down in the lower right-hand corner. He's not attached to a boom and has legs and will be able to walk and run in the free area. So he's just been unpacked from the box and is really just getting set up, but look for good things to happen from Marlowe. Maybe he'll have a demonstration for us at next year's Robotics Day. David Remy, who I saw around here earlier, is also working in legged robots, but more quadrupeds. You see a picture of a robot that he built during his PhD thesis in Switzerland, and he's very interested in how compliance in these types of legged systems can be used to enable better locomotion and control strategies and more natural human or animal-like locomotion. He's also interested in using these compliant mechanisms for rehabilitation robotics to help people recover from stroke and other injuries. Going to a completely different scale, we have Professor Oldham, who's looking at building micro robots. You see the very large scale picture there of the robot, and then you can see how big it is on the front of a penny, if you can see that very small thing. He's got a microscope over there, and I think you can go see some of his robots, but there really are a lot of challenges in building robots at this very small scale. How do the actuators work? You can't really build a motor, or maybe you can, and if so, how do you do that? You need to carry all your own power, and you need to integrate the controls together with the actuators and the sensors. So putting all these things together into a micro package is really an incredible challenge, but has a lot of potential applications, not just for robots, but for any micro devices, such as for the surgical techniques that were mentioned in the panel discussion this morning, and anything that you want to move precisely and controlled at the micro scale. I'm doing some projects in improving robot teleoperation, and you can talk to a couple of my students down the road there. But there are a lot of challenges when you're trying to operate a robot and you can't see it, and all you have is a joystick to control it. So we've looked at technologies including having a master-slave robot arm. So instead of trying to control each joint of the robot with a stick independently, you just move the arm where you want it to go. And also using augmented and virtual reality for better feedback from the robot to the user. We've started to do some work in optimization to try to make the remote robot operate as fast as possible in a safe environment, even in the presence of time delays. The time delays both from the robot to the user and back again. These time delays can really stack up and degrade the overall performance. On another level of human-robot interface, Professor Provost in the computer science department is looking at how can you model human emotion. So she's developed techniques that can look at the human who's speaking and just gesturing, and the computer can determine what the emotional state of that human is. And this can be really important for a human-robot interaction. If the robot can understand what's the emotional state of the human, they can understand the commands that they're being given in a much more rich environment. We can understand when someone talks to us what the tone of voice they're using and how we should interpret a command differently in that way. Robots right now, even if they can recognize speech, they don't have that capability yet to interpret emotion, but I think that's an important thing going forwards. So you can really kind of see the breadth of the different types of research, and obviously I didn't have time to go into any of them in depth. But we think, oh, I've missed one, sorry. That's why I don't have my up. So the last one I want to talk about is manufacturing robots, and this is about coordinating multiple robots in a manufacturing environment for improving energy efficiency as well as overall time in the lab. So a more classical manufacturing application and task scheduling. Is that the last one? Yeah. So you can see from the breadth of all these different pieces put together, we believe that we can bring together all these different robotics researchers and educators in all these different fields and put them into what we are calling a robotics institute, where robotics is really a big umbrella robotics. It will include manufacturing robots, autonomous vehicles, as well as human-robot interaction in all these different domains. And we think that these robotics will have a lot of applications in all different fields of engineering. And we're excited to see what the possibility is of going together and bringing people together in this area of robotics and not along the different disciplinary areas as we're traditionally aligned. So we think that the Robotics Institute will, of course, continue to participate in Robotics Day, as we're doing now, but we think there's an opportunity to start a new PhD program in robotics, where students will come in and instead of studying mechanical engineering, where they'll probably take dynamics and controls, but maybe also fluids and thermal sciences, they'll be able to take, mechanics or dynamics and control, and also artificial intelligence and computer vision, and have that breadth across the disciplines related to robotics. Similarly, students coming in with the more computer science aspect will also take artificial intelligence and machine learning, but also kinematics and dynamics as are appropriate to a robotics type of degree. We also believe there's opportunity to start an undergraduate minor or concentration initially, possibly leading to a degree in the future. And we've been talking with the dean about the potential to build a new building that would bring all of the 25 or so faculty interested in robotics together in one building, so that the aerospace engineers and naval architects and mechanical and electrical engineers interested in robotics would all be able to work together on research projects instead of having to traipse between 6 different buildings across campus. So that's a very brief summary of what's happening in the University of Michigan Robotics. And I say it's not a summary, it's a snapshot. I'd say this, you got one slide from fewer than half of the faculty on the list, but it's kind of gives you a breadth of the different types of activities that are going on. And so I think with that, I'll turn it over to, do I turn it back to you or I turn it to Phil? Okay, where's Phil? Then I guess we'll turn it to Vineet, and we'll see what happens next.
Right. thanks, Don, for that introduction. Since it's turned back to me, and I think we have a few minutes, why don't we take a couple of questions, if there are any, that maybe Professor Tilbury can answer for us before we break out. So would that be all right? Yeah. So yes, go ahead.
So the question is, the robot that can detect emotions, is the purpose to detect whether people are lying? So I haven't talked to her about that. That's a good question, and I should ask her. One of the actual ideas she has is to help autistic children be able to sense emotion, because that's something that they don't really sense very well, but to help them learn and understand about emotion that's coming on in their interpersonal communications. I think the research is still in its early stages, but probably has a lot of potential in many different directions. And now Phil is back and will take over the field. I'll be around all day and be happy to answer any questions. If you want to come find me, I can try to point you to the people. Or if you go to the website robotics.engine.umich.edu, you'll be able to find the links to all the different faculty. Thank you again.